Hello and welcome to this section of the MATLAB Tutor. Here we're going to dive into some really important functions that we constantly use matrices for. We're going to talk about determinants and inverses, which are really important. Before I get there, I want to talk about a few simpler things to understand. Let me create a matrix called A, and I'll fill it with data as follows. 3, negative 5, 3, 5, 5, negative 7, 0, 1, 2. So I have a 3 by 3 matrix here called A. Now, for those of you taking matrix algebra or have used matrices for a while, you have probably heard of something called the trace of a matrix. So if you pass a matrix to the MATLAB function called trace, what you get is 10. And what that is the sum of the diagonal elements. 3 plus 5 is 8, plus 2 is 10. So it's very straightforward. There's nothing much more to it. You take the diagonal elements of a matrix, you add them up, that's called the trace. So if you ever have a need to do that, you have a built-in function for it. There's also something that you probably studied if you've taken a linear algebra class called the rank of a matrix, and there's a built-in function in MATLAB for that. If you ever need to calculate the rank of a matrix, just pass it the matrix, and in this case you'll get a 3. Now, notice this is a 3 by 3 square matrix, so most of the time the rank of the matrix is just going to be equal to, the dimensions. In this case, it's 3 by 3, so the rank is going to be 3. But it's a little more complicated when the matrix is not square. You can't really predict the rank ahead of time. There's a way to calculate the rank. It has to do with figuring out if the rows and columns are linearly independent from one another, and by looking at what you get when you do that simplification, you'll figure out the rank. So if you're studying linear algebra, it's beyond the scope of this video session to teach you how to calculate the rank by hand. But if you're taking that in a class, you've heard of the rank before, you know how to do it by hand. This is the MATLAB function to calculate the rank of a matrix by hand, and that's as much as I really want to say about it, because to do it by hand, you have to do some manipulations of the matrix to prove to yourself the rank. So let me close that off. Let me teach you the determinant of a matrix. So let's go and calculate. Let's set up a matrix B, something that we can all visualize. 4, 5, next row, 2, 3. So here's this guy. To calculate the determinant of a matrix, which has so many applications, it's just DET, determinant of a matrix. You just stick the matrix in there, and then MATLAB calculates the answer is 2. So the determinant of this matrix is 2. And I picked a 2 by 2 matrix because the way you calculate it by hand is you do like an X. So it's 4 times 3, that gives you 12, minus 5 times 2, which is 10. So it's 12 minus 10, that gives you 2. So that's how you calculate the determinant of a 2 by 2 matrix. Now this other matrix we calculated is a larger matrix. To calculate the determinant of this, you can do it. It's not that hard. It's something I teach by hand when I do my lessons in circuit analysis and other math classes, because you use it so much. But in the context of MATLAB, you want MATLAB to do it for you, so you just pass it the matrix, and then it calculates the determinant for you using the rules of matrix algebra. The larger the matrix you have, the more involved it is to calculate the determinant. So a 3 by 3 matrix really isn't that hard to do by hand. But when you get into 4 by 4s, and definitely anything larger, 5 by 5, 6 by 6, anything bigger, calculating the determinant by hand is just a pain. So you need to do that, using a calculator or a computer like this. So you just pass it the matrix. Okay, and then finally, I want to teach you how to calculate the inverse. So here I have matrix A. To calculate the inverse, it's just INV matrix A. So you just have the function called inverse, INV, and you pass it the matrix, and what you get back is another matrix. When the thing that students sometimes get confused about is when you take the determinant of a matrix, you should always expect a number. That's what you get back, a number. When you calculate the inverse of a matrix, you should always get a matrix back. And by the way, the definition of a matrix inverse is such that if you take the inverse and you multiply it by the original matrix, you should get an identity matrix back. So we can actually do that. We can say original matrix A times the inverse of matrix A. Don't forget, this multiplication is doing, as this is a matrix here, this inverse of matrix A is itself a matrix. So you have a matrix times a matrix. So when you do this multiplication, you're doing matrix multiplication, row by column, row by column. And when we do this, we get ones. We get ones along the diagonals. Now you can ignore these negative signs here because what's happening here is, see, when MATLAB calculates the inverse, you see all these decimals everywhere. It's got to do some approximation somewhere. It's got to, it's got to truncate things along the way, and so these decimals that were displayed on the screen, they're truncated a little bit. So when you do the multiplication of the matrices, you get a little bit of rounding errors, and so this negative zeros, you just basically treat them all as zeros. So what you really should get back is diagonals with a 1 and zeros everywhere else. That's the definition of a matrix inverse. When you multiply it by the original matrix, you should get ones along the diagonal, and that's what we get here. So that's how you calculate a matrix inverse. Now, let me show you one of the most useful things in all of matrix algebra. I use it in all of my circuit analysis lessons when I'm solving the systems of equations by hand. I use matrices to solve those linear systems. So we already have matrix A. Let me overwrite matrix B, and we're just going to set it equal to something else. So matrix B, we're going to set equal to 7, next row, -8, next row, 3. So what we've really created here is a column vector or a column matrix. It's just got simply 3 rows in one column. So they're all on top of each other like this. So let me just make sure you understand. Here's matrix A, here's matrix B. Matrix A is a square matrix. Matrix B is just a column vector like this, or a column matrix, however you want to call it. So this is how you would write a system of equations, another way of writing a system of equations. If you can imagine matrix B being over here as another, another column, then what you'll have is, it should look familiar because I used the system of equations in a previous lesson. You'll have a system of equations. So A is what we call the coefficient matrix, right? So this represents 3x minus 5y plus 3z. This represents 5x plus 5y minus 7z, and so on for the third row. And then the B matrix represents what's on the other side of the equal sign. And so this is another way of writing a system of equations. So you have A times x is equal to b. So x being the unknown. So typically the way you would write that on paper is you have the coefficient matrix A times the vector x, right, is equal to b. That's how you would write it on your paper. So this is the coefficient matrix times some unknown values I'm trying to solve for, x, y. I'm using the letter x here to represent it, but it's really a vector, so it's x, y, and z. That's what I'm trying to solve for. And that equals what's on the right-hand side of the equal sign, which is the B matrix. This is all coming straight from a linear algebra class or a matrix algebra class, so if this doesn't make sense to you, then it's just because you haven't studied this before. But the bottom line is you can use matrices like this to represent a system of equations. And what we want to do is solve for x, just like we want to solve for x for any equation. That's what we want to do. It's just that x is going to represent 3 values, x, y, and z. Capital X is just a shorthand way of saying that. So we want to figure out a way to do that. Now, we already figured out that if we take A and multiply it by its inverse, all we're going to get is 1s along the diagonal, which is the same way as just saying you just get 1 back. So if we multiply this equation, both sides, by the inverse of matrix A, then on the left-hand side, we're just going to get 1s because A times its inverse is just basically 1. On the right-hand side, we'll get some answer. And then what we'll have is, since we have 1 on the left, it'll just be x is equal to whatever. So the way you would really calculate this is you would say the answer, which I'm going to call x, is equal to the inverse of matrix A times matrix B. So this is linear algebra straight out of the book. You have the inverse of the coefficient matrix times the B matrix, which is what's on the other side of the equal sign. You do this multiplication and you get some values for x. And x is a capital X. Notice there's 3 values in here. The top one is for x, the middle one is for y, the last one is for z. So then these are the answers. X is equal to 0.6466, y is equal to negative 0.0862, z is equal to 1.5431. And those are the answers. So if you had a system of equations, one way you could solve it in MATLAB is to make a coefficient matrix. This is the coefficients on the left-hand side of the equal sign of your system. You make a column vector of what's on the right-hand side of the equal sign, and then all you do is take the inverse of A times B, and these are your answers. Now this should look a little bit familiar to you because I solved this problem before. So let me tie the knot and show you a little bit closer. So we'll say system. We'll call it system is equal to, I'm going to put it all together. 3 space -5 space 3 space 7. Next row, 5, 5, -7, -8. Next row, 0, 1, 2, 3. So this is exactly what we typed before. Notice matrix A is this and matrix B is this. So what we have here, I've just created a giant matrix that has all of the coefficients right here, and then it has the column vector appended on the right-hand side. Now notice that this is exactly what I showed you a few lessons ago. I told you this was an augmented matrix. You've got the coefficients on one side, and you have like an invisible dotted line, and then you have what's on the right-hand side of the equal sign there. And I told you that if you represent your system like this, then you can just do row reduced echelon form, and then basically you get your answers. You can read it right off the matrix, because here you have a 1, so x is equal to this, y is equal to this, z is equal to this. So what we get is an answer by doing row reduction. You can read it directly off the augmented matrix. It's exactly the same thing as saying that x is equal to the inverse of matrix A times matrix B. Remember, matrix A is just the coefficient matrix, and you're taking the inverse and you're multiplying by this column vector, which is what's on the right-hand side of the equal sign, and notice we get the same numbers. X is equal to this, y is equal to this, and z is equal to this. So it's kind of a nice lesson to teach you that there's always more than one way to solve a problem. Which way is better? I mean, they're both the same thing, basically, or they're both equivalent ways of getting to the answer. If you want to represent the entire system of equations, including what's on the right-hand side of the equal sign, in your matrix, fine. You can do a row reduction, read the answers right off. If you want to have two matrices, one of them being a coefficient matrix and one of them being a what's on the right-hand side of the equal sign, you can use a matrix inverse and multiplication to get the answer, and that's going to give you the same set of answers. It doesn't matter to MATLAB. MATLAB can do it both ways. Usually by hand, what you prefer to do is this way. Because you can usually use your calculator to find the inverse and then do a quick multiplication and then you get your answers. Doing this row reduction by hand on paper and showing your work could be a little bit of a bear. But when you're dealing with MATLAB and you're using a computer anyway, you have your freedom to do it either way. I just wanted to show you how you would use the matrix inverse for a practical reason. So we're done with this section. We've covered a lot of material. We've covered how to find the trace of a matrix, how to find the rank of a matrix. We've learned how to calculate the determinant and also how to calculate the inverse. And I've tried to tie this together with previous examples to show you how you can basically tackle a problem more than one way using MATLAB.